All right, today we're going to talk about essentially the graphing and the transformations of logarithmic functions. All right, so the very first thing you need to know, and by the way, I'm on page 168, so make sure you go to page 168 to do this. The first thing you need to know is that every logarithm has a vertical asymptote, precisely at x is equal to 0, and the domain is normally from 0 to positive infinity, the 0 representing where the vertical asymptote is located. And then the range is actually all real numbers. Remember, the range is how far down or how far up this graph is going, all right? So again, in generic terms, the vertical asymptote is always at x is equal to 0. The domain is between whatever the vertical asymptote is to positive infinity, and the range is from negative infinity to positive infinity. All right. So I think if you have the Desmos calculator, if you happen to have your computer open, I think that would help a lot. But if you don't have it, that's okay. I'm still going to teach you how to do this by hand anyway, at least partly, all right? So, all right, like we said before, right, it doesn't matter what the logarithm is. In this case, the natural log, all right, the natural log, which remember, this is the log base e of x, would similarly also have the same domain as I have previously talked about. Now the domain is it's not always going to be from 0 to infinity. And I'll explain when that's going to be different. But as far as the range for a logarithm, all right, the range will always be all real numbers from negative infinity to positive infinity. Now if I graph the following functions, I'm going to talk about how to graph them, all right? But essentially, when you have, like, for example, log base 10 of x, what I would do is I would start off by saying, okay, instead of coming up with points for the log base 10, I'm going to come up with points for the inverse, which is 10 to the power of x. So if I do a few terms like x and y, right, and I just start picking up numbers, like, for example, 1, or let me start at 0. Right, anything to the 0 power is 1, 10 to the first power is 10, 10 to the second power is 100. All right, so again, but for the logarithm, because they're inverses of one another, the log base 10 of x will be, the x's and y's are actually going to be reversed. And all the x's right here will become the y values. And all the x's, or all the y's, will become the x values for the logarithm. So notice again that all I've done is I really just swapped them, all right? So if I were to graph that, okay, I would have 1, 0. Remember graphing the stuff that's blue. So 1, 0 would be right here, and then really the other one that I can graph would be 10, 1, which is right here, and obviously I don't have space, but in general, you must know, again, that this has a vertical asymptote, all right, at x is equal to 0. And this logarithm is going to get really, really close to the vertical asymptote, but it will never go through it. And it's going to look like this. Now, if that looks semi-familiar, hopefully it does, it's because that's the inverse of an exponential. So it kind of looks like an exponential function laying on its side. All right, so that's it for that. Now, how would this look any different if it was log base 3? Well, for a log base 3, all right, again, I'm going to go back over here and say, okay, I don't know where that is, but I can come up with x and y values. All right, x and y values for the exponential function, So what I can do is I can raise that to the 0 power. 3 to the 0 power is 1. 3 to the 1 power is 3. 3 to the second power is 9. And for the log base 3, I would have the same numbers, but the x's and y's would be switched. All right, so if I grab this in green, notice that again, I have the same point 1, 0, but then I have, let's see, 3, 1. And then I have 9, 2. 9, 2 would be like right here. And again, I would get really, really close to the x-axis, to the vertical asymptote, to the y-axis. but I'm not going to go through it, all right? Then finally, last but not least, the log base, the natural log, right? That one I'm not going to put the points in there, but it would be the same thing, except for this would be a little bit higher than the last one, right? And remember, the natural log is log base E, all right? So that would have Euler's number, which is 2.7. So the question on here is discuss the similarities and differences, right? Similarities between all of them. All right, so let's write those down. Well, they'll have the same vertical asymptote. They'll have the point 1 comma 0. In this particular case, the domain and the range are all the same. Let's see. And of course, the shape in general is the same. In general, that is. All right. Notice that I'm saying the same shape. I didn't say that they look exactly alike. Now, the difference, there's not a whole lot of differences, but I did notice one difference, and hopefully so did you, that the bigger the base of the logarithm, for example, at 10, all right, the smaller the growth, all right? So the bigger the base, right, the bigger the base, the smaller the growth. All right, I see this is lagging a little bit. Hopefully it'll make it through. That one is like wiggling. Oh no. All right, it's alive. It still works. Now, on this one, I'm gonna use technology, all right? And by technology, I would say I'm gonna use Desmos because honestly, that's the easiest thing you can use, and I think is the most graphically, easier to do. All right, so if we look at, if I plug in exactly what you see, f of x is equal to the log base a of x, right? So I'm gonna go to my Desmos app. You can do it on your own if you want to or not. I've already graphed this. Hopefully it didn't. Oh. I spoke too soon. I'm gonna have to delete this. What a shame. All right, but it won't take us any time to do it. So I'm not gonna type in exactly f of x. I'm gonna type in y equals, and I'm just gonna type in log. And I am gonna put an a. And if you do this on Desmos, it's actually automatically gonna ask you to see if you want a slider, right, for a, and you just have to press that button that says add a slider. And then notice what happens, right? The notes are asking what happens when a is positive, and you can actually see a, it's almost like a vertical shift, which is weird because normally that's a horizontal stretch, all right? And then notice when a is negative, it actually makes it a reflection over the y-axis, all right? So that's what's going on there. So let me go back to my notes. Hopefully this will let me without too much fuzz. All right, so we're gonna write that on here. All right, a is a vertical shift. Or at least that's what it looks like. Normally what that does is a horizontal stretch, all right? If A is big, it actually makes it a horizontal compression. If A is really small, it makes it a horizontal stretch. But anyway, at least that's what that looks like, all right? So we're gonna move on. Again, A, I'm gonna say is a horizontal stretch or compression. Now, don't worry too much about this because the horizontal stretch or compression, all right, is actually something you're gonna deal with more in pre-cal, not necessarily in Algebra 2. All right, this one, however, it is fair game, right? So if I see this, right, and think about all the transformations you have done in the past. What happens when you have an x plus a constant? What happens to the graph? Well, if you can remember, let's see. All right, so I'm going to delete this one right here, or I'm going to change it at least. All right, so I'm going to put a plus c here. And again, normally automatically, as soon as you put a C or an A or a B, it asks you to add a slider, so we will. And then let me press the home button so I can recenter the graph. And then notice, if C is positive, what happens to the graph? All right, notice that it's moving left. If C is negative, it moves to the right. So it kind of goes back to what we talked about, how C or your X is a liar, right? But remember, the reason that happens, right? The reason that happens is because if you set that inside, for example, let me see where my pencil go. Let's just give you a specific example, right? And I will take this opportunity just to kind of teach you how to graph this, right? Say that I want to graph log base 2 of x plus 3, right? And I'm picking log base 2 because that's a small enough graph that I can actually graph a few points. Now, if I set that inside, which is x plus 3 is equal to 0, that would actually give me a shift to the left by 3. All right, so what that really means to you is that my vertical asymptote has moved to the left 3. So first and foremost, I'm going to do that. I'm going to put my vertical asymptote right here. Now remember, there is no point that goes on the vertical asymptote, right? Now, what we're going to do next is that we can say, if we want to graph this, right, we can say, okay, what is 2 to the x power? And I want to plot a few points for that. If x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 4. So remember, all I'm doing is plugging this x values here to figure out what the y value is. All right, and I guess we can put one more. If I put that, we have an 8. All right, so what happens here is that on the log base 2, right, on this log base 2, the x and y values are going to reverse. So this is going to be a 1, a 2, a 4, and an 8. And we have a... And by the way, that's not completely true. This actually would be log base 2 of x, right? That would be before adding the 3 to it. So let's see. I have a 0, a 1, a 2, and a 3. So I can do this 2 ways. You choose whatever way you want or you like better. But if I'm graphing this, one way to do this is to say, okay, if this right here, I'm putting a tiny little cross right there. If I pretend that's 0, 0, the first point I'm going to put on here is 1, 0, which is right here. Okay, and then I'm going to go to my next point, which is 2, 1. So if I pretend like that little cross is my origin, notice that I'm saying pretend. It's not the origin, but I'm going to pretend 2, 1 will be located right here. All right, and I would go to 4, 2. So let's see, 1, 2, 3, 4, 2. Right, so that would be 4, 2, and of course I would do 8, 3, and so on, right? So remember what that would look like in general? It would look like this, right? And it would help you if you just generally remember what the logarithm graph looks like, right? Another way to do this, right? If you don't like this, you don't like the whole fake origin thing that I'm talking about, and you're forced to graph this by hand, which you might, because I think half of your test is without a calculator. All right, another way to do this is, for example, to remember how I said this was -3, right? If you subtract 3 from the x value, notice that I'm putting a plus there, but and if I were to create another table, right? This table that I'm creating now would be the actual, would be this table right here. that would actually look like a -2. Let's see, this would be a -1, this would be a +1, and this would be a 5. The y values would not change though. And then notice that what ends up happening is that these points right here is exactly what I graph without having to do any trickery. So by pretending something is the fake origin, that table is the true table that goes with log base 2 of x plus 3. All right, moving on. This one, I'm not gonna just kill you on it. However, let's just see what happens on Desmos, try to take a guess. All right, so I'm gonna change my Desmos calculator and I'm gonna change that just to a -x, and you're about to see what happens here pretty quick. All right, what happens is that you end up with a reflection over the y-axis. And again, same thing now, this is a little bit different. If x is positive, it does move to the right. And if C is positive, it moves to the right. If C is negative, it moves to the left, like it should. Now, it goes back to what I said earlier to you, that if you want to know if something's moving right or left, set this inside of the logarithm. And let's just say this C was a number that we can kind of deal with, so it's not hopefully too confusing for you. Let's say that was a -x plus 2. Well, in that case, and if I set that equal to 0, I will get x is equal to 2. So that is a true value, all right? So that would actually move. If I had the same graph, for example, but this would be instead of, all right, if I set that equal to 0, I would get x is equal to 3. Right, which means that my vertical asymptote would be at 3. And it would be a reflection over the x-axis. So what would happen here, oh Lord, what would happen here is that the x values would be the opposite sign of what I have. But I'm not going to do that just for the sake of time. And probably this one right here, I bet you probably know what happens. So for example, if I have a log base 2, so I'm going to keep kind of playing with the same numbers, right? And I have x plus some number, and let's say that that number happens to be plus 3 on the outside of the parentheses. What do you think is going to happen to the logarithm? All right, so let's go look. So again, same type of problem. But I'm going to write a plus k here. Let's see if it likes that. All right, I'm going to add the slider. Let's press the home button so we can recenter the graph. And again, if k is positive, it moves up. If k is negative, it moves down. Okay, and as you can see, that's what would happen. And we can let it play. Let's see what happens. So again, if k is negative, it goes down. If k is positive, it goes up. All right, so let's see if this will let me actually graph it. Oops, excuse me. Let's see if this will actually let me graph it. Okay, so if I wanted to graph this, remember, I still have the same table that I had earlier. I'm talking about this original table, the 102.14283. All right, so remember how I got it, hopefully. Oops. Let me switch colors on you. So the x and the y value of the log base 2 of x was 1, 0. Two, 1, 2, 4, 8, 3. Right, so what would happen when you have the plus 3, right? First of all, the vertical asymptote did not move right or left, so that's going to stay in the center. Right, at x is equal to 0, so that's not going to move. However, what I can do is that this plus 3 right here is going to add 3 to all the y values. Okay. So now my new table should be 1, 3. So at 1, 3, I would be about right here. Then my next point should be 2, 4. My next point should be 4, 5. And we can kind of leave it there if you like. And again, don't forget that the shape in general looks like this, hugging the vertical asymptote, and it goes like that. All right, so that's mainly all you need to know for this. So if you have any questions, all right, make sure to first try to do the Delta Math homework and look at those videos that come with it. And other than that, well, actually, I don't even know if we have Delta Math homework for this. No, I don't. This is actually paper homework, so my bad. If you have questions, I guess just reach out to me as soon as you can, and I'll try to answer it, all right? We'll see you next time.